So welcome back for the second session, and we are happy to have Mehrdad again. We'll continue on boundary actions and applications to C-star simplicity.
Thank you. Okay, so I was in the middle of proving in a concrete case unique stationarity of the canonical trace on the reduced algebra of the free group. So let me get back to that, finish that argument. So I want to show in this concrete example that for the choice that you the canonical symmetric quality measure new I mentioned that it's a fact that then there is a unique mu stationary probability measure on the boundary of the free group, and the boundary of the free group this is the Poisson boundary of the random walk on the free group with this probability. In fact, these facts, I mean, you can choose any finitely supported symmetric probability measure on the free group whose support generates the group, and these facts are true. There's nothing special about this choice. And then so the argument we were making. Then I wanted to show you that then the canonical trace is the unique stationary mu stationary state on the reduced algebra of the free group. So I started with the mu stationary state on in here. And now what I want to do is to show you that this vanish at any non-neutral element. That's the argument. And again, I want to use this proximality that I have. Now here, I have a little bit more. So the proximality that I have here, because this is also a boundary in the sense, in the measurable sense that Hannah discussed in details, it is true that I can contract any probability measure to any point, which is the definition of a topological boundary. But now I have more control. I know how to actually do that. I can, particularly for this particular measure, I know how to do that. If I start from here, if I want to contract it to a point, I should just go along the path of my random walk. Every path in a random walk converges to a point. If you translate this along the same path of the random walk, you will converge to the Dirac measure at that point. So I do know how to do this, and this is what I want to exploit to overcome the issue that, if you recall yesterday, if I started from a trace, the argument was, okay, start from a trace, extend it, restrict it to the other side, the copy of C of x, use the boundary property to contract that to a point. When you do that to the extension, this translation does not disturb the original trace because it's a trace. So you can play around with all extensions without disturbing your original trace. That was the key argument. But if I'm not a trace, if I take an extension and I start to translate it, then my original state will also keeps moving. So I need to know where does it move. And as I mentioned yesterday, the key about the stationarity is that you will know where you end up at the end, at the limit of these translates if you do the limits along a path of the random walk. Okay, so let me formalize all these sentences. Let tau tilde be a new stationary state on B of L2 of F2 that extends tau. We said this always exists. Then if I restrict this to the copy of C of x, now from this point on, I'm going to identify continuous functions on the boundary with its copy inside an infinity of F2 that we defined yesterday, and Jacob also reminded you. So this is via the Poisson transform, if you like, and this is also identified with its image inside P of L2 of G. So I'm considering this as a sub C star algebra of P of L2 of G, which is invariant under Le, so the conjugation by the regular representation gives you the action of F2 on this space.
So G is F2.
Say it again.
G is F2.
Where is G? Oh, G is F2. Oh, of course. Thanks. So this is mu stationary probability. So by the uniqueness that I mentioned, this restriction is just nu. So tau tilde is the same as nu. Okay. Now, for almost every path of the random walk, let's call it omega, I know that Gn nu converges weak star to some delta measure. So this is basically the definition, if you like. The definition of a mu boundary is that you have this, and the fact that, as I mentioned, this is a mu boundary tells me this for some point x omega in your boundary. Okay, now this is what I like. Passing to subsequences, if you like. We get, so now I apply this to tau tilde. Gn tau tilde would converge to some tau tilde omega. And again, weak star for almost every path. And I mean, just, okay, it's fine. And now, by the uniqueness of all these, when I restrict to continuous functions here, this is that. Okay, so then the same, or similarly I should say, similarly the same happens for my original so I should have said, should quantify here for some tau tilde omega, some state on B of L2 of F2. I don't know what state it is. And this also happens for some state tau omega on the reduced algebra of F2. So I have a bunch of, in fact, I do have one single stationary state on top, and then I know every stationary state, as I mentioned the proposition last time. So if you translate it along a path of the random walk, you always converge weak star to some state. And you do know that state when I restrict to the continuous functions on the boundary part. It's a Dirac measure. On the other side, it's something I don't know what that is, but it's some state. But now I am in the position to apply the very first lemma I mentioned when I started my lecture last time. And that is, whenever you have a state on B of L2 that restricts to a Dirac function, to a Dirac measure, then it will kill any group element who moves this point. So, by the lemma from yesterday, tau of lambda g, which is the same thing as tau tilde, tau omega of lambda g, which is the same as tau tilde omega of lambda g. You see, I mean, this restrict to that. This is by just the way that I took the way that they are defined. But this must be 0 if gx omega is not x omega. So now, let us ask ourselves, so now let's consider the action of the free group on its boundary. And I'm taking a non-neutral group element. So there might be points, I mean, there's always points that it fixes. But how many are those? I mean, how big is the fixed points of a group element acting on the boundary? So in fact, it only fixes 2 points. Now, it is also a fact, really not difficult to sit down and convince yourself and write a proof that mu stationary measures cannot be, they don't have any atom. They are, as you call it, diffuse. So they don't have any atoms. Which means that the measure of the fixed points of any non-neutral group element is 0. Which means that if G is non-neutral, and these are just facts about the dynamics of the action on the boundary, the measure of the fixed points is 0. So every non-neutral group element will do that for almost every point on the boundary. Okay, so tau tilde of omega of lambda g will be 0 for almost every path omega in your random walk. And finally, as I mentioned in the proposition from last time, so it is not only that I know. It is, so the point of stationarity is not only that the limits exist when you translate along the paths. Perhaps the more important piece is that you can recover the original one from the limiting points by integrating them. So I do know that this is nothing but the integral over the whole path space of tau omegas of lambda g's d omega. And so I guess I'm just referring what this means to Hannah's lectures.
I didn't give, I only really considered the case where we got to deluxe. I didn't give this formula.
Okay. So the, but there is a canonical measure on the space of all paths that govern how likely you are to take a path versus another path. So I'm integrating with respect to that, and that and that is so. And also there is obviously a map from the space of all paths to the boundary, which sends every path to its destination. And the measure on the boundary is the push forward of this measure. So this can be, so this is, if you like, you can translate based on everything you know. So you can translate into, so this is basically like this. Okay, maybe I write the formula here. So if you give me a function f in C of the boundary, and this is for any boundary if you like, d nu x, this is integral of f, and let me say pi of omega d omega. Now pi is the canonical map from the space of all paths, which is f2 to the power n, with the measure that governs how likely you are to take a path versus the other one onto the boundary of f2 with mu. So this is, so you have a map from here to here, and this is the push forward, and you have this. So these are not the things that, so these are facts from the theory of random walks and boundaries of random walks. Okay, but now I know that this happens. So this will be, this will be 0, because these are 0 almost everywhere. And that ends the proof. And all I needed to run that proof were the fact that I had this boundary that was boundary in the measurable sense, and so the measure that made it into a mu boundary, a boundary of the random walk, that was the unique stationary measure on that compact space that made it a boundary of a random walk. And the last piece, I needed the action on this measurable space to be essentially free, the fixed points of any non-neutral group element to be a null set. Whenever you have that, you can run this argument, exact same argument, and it gives you uniqueness in this sense. Hence, as I mentioned yesterday, it gives you simplicity of this reduced group system algebra. There are tons and tons of, this is not about it's something special about the free groups. Huge class of groups have such actions. Now, one thing that you may notice is that, again, in this proof that I ran, I used proximality in the sense of measurable boundaries, random walks. So if you notice, I did not really use the fact that the boundary of the free group was topological boundary in the sense that I defined yesterday. I used that it was a boundary in the sense that Hannah defined, with the addition that this measure is the unique stationary measure. But in fact, you can prove that any measurable boundary for which this probability measure is unique stationary, the underlying compact space must be a boundary in the sense I defined yesterday. So it is one of the boundaries from yesterday, but with some additional proximality properties. Okay.
But you can use, maybe you're wrong, but you can use the topological boundary also to give this proof, right?
No, to prove what?
The sister simplicity.
Oh yes, no, I'm not doing sister simplicity. I mean, that's a consequence of that. I'm proving uniqueness of a stationary state.
Yeah.
So, in general, I mean,
with similar arguments, right?
it's a similar argument, and that's my point. I wanted to show you the similar argument used to prove similar results. So this time, my object is a state with this additional data that it's stationary, and I want. So what I'm proving is it vanishes on group elements. I mean, whatever comes out of it comes out of it, right?
So can I ask you? Do you know if these stationary measures are give alignment systems in the sense of Fuhrmann?
In this case, it does.
But
Whenever you have unique stationary boundary, yes.
Okay.
You get alignment system. Okay, good. So let me now do a third. I wanted to also do a third example of results where, again, I'm going to do similar tricks to prove type of uniqueness of certain other maps. In particular, certain maps vanish at certain group elements in a unitary representation. Okay, so here, this time, I want to consider unital positive maps rather than just states. So let me take a point, and I'll do this argument for this very specific dynamics, but this is, again, I comment that I'll comment this. You'll see this can be generalized to setups. I take a point in the Furstenberg boundary that I defined yesterday, and let, say, H be the stabilizer. So all the group elements who fix this. Now, Let us, let pi be the representation of G on L2 of G mod H. Just by translations, this is a quasi-regular representation. And I want to also embed continuous functions inside B of L2 of G mod H as follows. So maybe I give it a name as before. So I say rho of f applied to, so the basis for this is this, let's say delta th. I define it to be f of tx delta th. And then you'll see that then this is a covariant representation in the sense that rho of gf is defined. This is pi g rho f pi g inverse. So this is one of the representations. I mentioned this yesterday, but let's repeat. Now, okay. So now it happens that unless H is trivial, which we know when does that happen. So if H is not trivial, then the C-star algebra generated by the group here will have no trace. So the first argument I started yesterday to take a trace on the reduced C-star algebra and then you can show something, that is out because there's no trace to begin with. So if I want to say something about, say, ideals or whatnot, then I have to either do the stationary version, but then the stationary version, as you saw, it is very good if I know the group, I know its random walks, I know something. But if not, then that is also out because, I mean, in general, unique stationarity, etc. This is true in many examples, but this is not something universal or general for any group. Now, this time, what I'm going to do, I'm going to again look at maps who always exist and try to. So a type of maps that do always exist are equivariant maps into. So let psi from B of L2 G mod H to continuous functions. I think I'm going to just take it as a fact at this point for the sake of time. Be a unital positive G equivariant map. Such maps do always exist. Take it as a fact. In fact, another way of defining what this is, or say another way of defining what this is the smallest compact G space such that for any C-star algebra with a G action, you do have a unital positive equivariant map from that C-star algebra with the G action into continuous functions of that compact space. So this has the property that these always exist. And this is the most efficient one. This is the most economic space that allows you existence of such maps. It could be, you could take it as a definition of what this compact space is. Okay. Now, what can I say? Two things. All right. So let me take G to be in G, and let me take little y in the boundary in here. Let tau be delta y composed with psi. So this is a state. This is a state on B of L2, right? And map, I should have said one additional thing here that extends if you like, rho inverse from rho of C of the boundary, I should say that, to I apologize, another fact that I'm just going to say it is true, but it is true. I said this is the smallest one that you always have maps into, but in fact further. So it is injective in the sense that any map that goes into it can be extended. Okay, so this map, I mean, this is the obvious inverse of rho. This map is equivariant, unital, and positive. Therefore, by the properties of this space, you can extend it to a map with similar properties from here to here. Okay. Now we have, what do I know about tau restricted to the copy of, so let me just write it, rho of f is what? For f in C of the boundary. So this is, so psi applied to rho of f is just f, and tau, and then delta y applied to that, so this is just f of y. So this is the Dirac at y applied to that. So if g moved y, so if gy is not y, then I know that this tau must kill that g, because the restriction to the copy of continuous function was Dirac at y. What does this tell me? That tells me that the map psi so psi of pi of g must be, okay, so this support, so this is a function on the continuous, this is a function on the boundary. This must be supported on elements that are fixed by g. That much I know. So outside the fixed point, it vanishes. Good. Now, the nature of this particular representation allows me to also tell you something about what happens inside the support. Now, inside the support, I'm going to show you that it has to be constant 1.
Sorry.
Yes.
It's inside the what? The fixed points of the G action on.
Yeah, so this is the x in the bound. So I fixed that. So z in the boundary
Okay.
such that gz is z. Good. Observe. For every f in here, if I have a function whose support is contained in the fixed points of G, we have, okay, let me observe myself. We have, if I look at this operator, so the composition of these two operators on BFL2 of the coset space. Now let me apply this to a coset. So by definition, this is just going to be f evaluated at tx, and then times delta gtx, gth. Now, if gth, if this equals to th, and okay, and so let me write this also on the side so you see. So this is by definition is just f of tx delta th. Okay, if gth equals th, then these two are the same. If gth is not equal to th, this means that G does not belong to THT inverse. But what is THT inverse? What is H? H was the stabilizer of the point X. So this will be the stabilizer of the point Tx. So G not being in here, this means Tx is not fixed by G. So F will kill it. So either GT is T and these two are the same, or GT is not, GTH is TH and they are the same, or GTH is not TH, both are 0. Either case, this equals to that. So, pi of G rho F equals to rho F for every F that is supported inside fixed points of G. Then I apply my map psi to the whole thing. Then psi of pi G rho F is psi of rho F. So, well, this is just F, because psi is just the extension of the inverse. Now, one thing I know is that this map psi is unital and positive, and when I restrict it to the copy row of C of this, it's identity, right? I mean, it's not identity, but it is multiplicative, you say. So it is a well-known fact that when this happens, the piece that on which you are multiplicative, it is also multiplicative with respect to the rest in the following sense. In the sense that you can split this into psi of pi of g times psi of rho of f. That's because psi restricted to the copy to the row, to the image of rho is multiplicative. But then, and that's also a general C-star algebra fact. So this means psi of pi of g times f equals f for any function f that is supported on the, okay, now, so choose f with, okay, so let this time y be in the fixed points of G. Choose f with support of f inside a fixed point, and f at y equals to 1, or anything non-zero, doesn't matter. Then you apply y to this equality. So now this applied to y. What does it give you? So on this side you are 1, on this side you are psi of pi of g. So psi of pi of g must be 1. Apply this, we get psi of pi of g applied to y must be 1. So all in all, I write the last conclusion here, so I know what psi of pi of g is. So psi of pi of g must be the characteristic function of the fixed points of G. In particular, you have only one such map. And this also shows you what I said at the beginning, that if some G has non-empty fixed points, then obviously this map is not the same as the canonical trace, and this is the unique map that you may have that has that property, so you don't have any trace to begin with. Okay, good. Now further, I'm going to now use this to show you that the C-star algebra that this generates, first, well, two things. If the C-star algebra generated by this representation has a trace, then this map must be that trace. And using the proof from yesterday, as I mentioned, you can run the same proof to show that if you have a trace, the trace must be the canonical trace. That argument works. So what does it mean for this to be the canonical trace? It means that this must be 0 on any non-neutral element, which means that the fixed points must be. And anyways, what it gives you is that C-star algebra we're talking about is the reduced group C-star algebra. Or at least let me just say that. This representation weakly contains the regular representation. That much is immediate. So that's if you have a trace. If you have a trace, you will have the canonical trace and you weakly contain the regular representation. In fact, a little bit more, you can show it is the regular representation. If you don't have a trace, otherwise, if you do not weakly contain the regular representation, it's the same as not having a trace. Good. And now in that case, I'm going to show you that this is always simple, so there is no ideal. How am I going to show you? I'm going to show you that if you have a representation that is weakly contained in this representation, then I'll show you that the characteristic function of the subgroup extends to a continuous state on the C-star algebra generated by that representation. This representation, by the way, is the GNS representation of the characteristic function of the subgroup. So a representation weakly contains this if and only if the characteristic function of the subgroup extends to a continuous state on that representation. So that's what I'm going to show you. So now suppose I have a representation sigma, a unirep of G, such that sigma is weakly contained in pi, just in case this was not mentioned or you forgot. So i.e. You have this surjective map from C star algebra generated by pi of G onto the C star algebra generated by sigma of G, a canonical one that sends pi of G to sigma of G. So this, the C star algebra this generates is a quotient of the C star algebra this generates. Suppose you have that. And I'll show you that this must be injective, let's say. Okay. Then, so what do I call this map? Let me call it phi. Then phi extends to, I still denote it by phi. I don't want to add a tilde now. From B of H pi, all bounded operators on H sigma. And you can extend it. So this is a star homomorphism between C star algebras. You cannot extend it to a star homomorphism, but you can extend it to something that stays unital and completely positive. Unital, completely positive. Now, I'm sure positive means, so unital, unit goes to unit. Positive means positive operators go to positive operators. Completely positive means the following. So when I have a map from here to here, then this map also gives me a map from all n by n matrices with entries coming from here to all n by n matrices with entries from here. And I require that for any n, the corresponding map from n by n matrices to n by n matrices to stay positive. But you can I need that only to use a property that I mentioned here, that if I know I am multiplicative on some sub-piece, then that piece behave multiplicatively with respect to the rest as there. That is true when you have a completely positive map. It does not work if I only have just positive. Yeah, I apologize. These are C-star facts that I'm going to just assume and go on. Okay. Then I had this. You recall? So I'm going to show you that I have a similar formula on this side. Then phi of pi g rho f is because I told you that I needed that complete part to say that now this will split. So this will be phi of pi of g times phi of rho of f. And that's going to be, now this is just extending this map. So this is sigma of g phi of rho of f. Good. And this must be the same. So this will be the same as phi of rho of f. I'm just applying phi, this capital phi, to this equality. All right. So I have a similar equality on this Hilbert space. Good. So I can repeat the proof that I did. Exact same proof. I mean, if you noticed the previous proof that I showed you, the only map such psi is this one. What did I use? I needed this equality. I mean, the fact that I have a copy of the boundary, continuous functions on the boundary, I have an invariant copy of that inside B of the Hilbert space, allowed me to show outside of these fixed points I'm 0. That's very general. That's what we did yesterday. To say that inside I'm constant 1, I needed this equation. Whenever I have this equality, I can prove to you that inside the fixed point you're constant 1. Whenever I have a copy of the boundary, I can show you outside that I'm 0. And for this representation, sigma, I have both. I have a copy of the boundary by just applying phi because you have a copy of the boundary here. This will push it to a copy of the boundary here. You can complain that how do I know this is multiplicative, etc. That's a valid point. But again, if you go back to the arguments from yesterday, I don't need it to be a multiplicative copy. But let me push that under the clock. And so I just say exact same argument. So exact same argument shows that shows that there's unique, but let me just say the map that sends sigma, that there is actually unique unital positive G equivariant map. Let me this time call it phi from the C-star algebra generated by sigma to continuous functions under Furstenberg boundary, such that now I know where does this go. This goes to the constant functions of the fixed point. The same map. Okay. Now, finally, let me compose this with the evaluation at point x. So, tau, which I defined to be delta x, and this x is the x that I fixed from the beginning where I defined h. H was the stabilizer of that x, so there was an x fixed from the get-go. So this C is a state on this is the algebra Good. And what is the value on every G? And tau of sigma of G is what? As we computed, is either 0 or 1. And it is 1 if x is in the fixed points. So this is 1 if x belongs to the fixed points of G, and 0 otherwise. But what is this? X belongs to the fixed points of G. That's the same thing as saying that G is in the stabilizer of X. The representation pi is the GNS representation of this function, So it follows that pi must be weakly contained in sigma, which means that you have the inverse map as well, is well defined and the star homomorphism. Therefore, this must be an isomorphism. Therefore, you don't have any non-trivial quotients. So, C star algebra generated by pi is simple. So, again, now I needed something extra. This extra thing was about the representation. So so the piece that I'm 0 outside was very general. I needed a copy, but the piece that told me that what am I inside, that depended on the type of representation. And again, this generalizes to a large class of representations. So maybe I finish by saying, okay, so particularly this last piece is the results I did a few years ago with joined with Eduardo Scarpo, and now.
So did you meet him?
Not yet, no. I have one of my students now is pushing this further to get more and more representations for which we could determine at least simplicity, or maybe further say something about the ideals. Okay, maybe I finish by saying what he has managed to do so far. He has been able to push this a bit further to say if so in this example, what is pi? The regular representation, the quasi-regular representation over H is just the induced from H to G of the trivial representation of H. So you can do a little bit more, and that is induced from same result for I being induced from a subgroup, I mean the same H, G of a character on H, but not any character. A character on H is a character on H that extends to a conjugate invariant positive definite function on G. So yeah, I mean this extends to the trivial, to the constant 1 on G, which is...
So character, you don't mean indecomposable?
No, no, it's just a, but character, I mean, okay, I have, so this is just a homomorphism to, from
okay,
to, I mean, the classical sense, sorry, yes. Yes.
So a multiplicative character.
Yes, multiplicative character, exactly. And yeah, I realized when I wrote this, I wanted to say character here as well. But, yeah, a multiplicative positive definite
character.
The sense of, but some that you can extend to. I mean, this one I don't want it to be characters. Anything that is conjugate invariant, positive definite function. In fact, I don't need it to. I think, yeah, don't need it to be positive anyways, but it's just okay. Yeah, so this will be this result when I apply this to the constant function 1, which obviously has constant function 1 as an extension, or you can start from any character in this sense of the group if it has it, and then restrict to H, and so on. Can do a little bit more than that, but it requires me to then define something. So I think I had 1 over and I went over. Okay, I'll stop here.
So probably it's already in your paper, I don't remember. But I think that something similar should hold for Koopman representation, right?
Yes.
So can you prove C-star simplicity in some cases?
Yes.
For example?
For the Koopman represent. Okay. Okay. What this argument basically proves to you is that that representation, the uniqueness of this map was the result, and therefore I have its kernel, I mean left kernel as a UCP map. That in this case it is an ideal, and that's the same spirit of results that a unique maximal ideal. And the quotient is the symbol. Whether this is faithful or not depends on the type of representation. But what you can prove is for any Koopman representation on the boundary, on any boundary, you have this unique map. Now, so for Koopman on the Furstenberg boundary, you get simple, that you get. But you can run the same proof. I don't need a Furstenberg boundary. I can do any boundary and any stabilizer. But what you cannot prove, it is not even true in general, is that it is the unique map is faithful. That is not true in general. But we have a sufficient condition for that to be faithful. So, yeah. The point about the Furstenberg boundary was that every stabilizer, which I don't know, nobody complained, but I wrote a continuous function being supported on fixed points of G. So I used the fact that in this particular case, fixed points of every group element is a Klopen subset. It's both open and closed. And this simplified some of the notations. I chose the Furstenberg boundary because of that property. In general, I can do the same for any boundary. Here, yeah, I cannot write that. That if this has empty interior, this doesn't make any sense for a function to be supported on that.
There are no more questions. Let's thank Mehrdad for
This is the end of this week program, so thank you organizers for that.